everything that we do to make sustained human presence on the moon, we're going to then apply to Mars. You know, they say it in Star Trek, it's the final frontier.
We feel really confident that when we touch down on the moon, it's going to be a safe and soft landing.
It's been over 50 years since humans have had a presence on the moon. But not only will we be walking on the moon again soon, private space companies are also working on lunar missions. You're going to start seeing and hearing about a lot of them as we establish a permanent presence on the moon over the next few years. Firefly Aerospace in Texas is one of the companies working on a lunar lander mission.
Hey guys, I am just north of Austin, Texas, and check out where I am. I'm here at Firefly, and I was able to get a tour, and of course, 2022 was a great year for Firefly. They had their first successful orbital launch.
On October 1st, 2022, just after midnight, the Firefly Alpha launch vehicle lifted off from Vandenberg Space Force Base in California, successfully reaching orbit and deploying customer payloads.
Seeing that thing finally lift off the launch pad and make it all the way to orbit was huge.
Having a lot of my literal blood all over the pad from all the times I got cut and scraped, just seeing it launch a rocket flawlessly into orbit was a true high.
This made Firefly the first company to launch and reach orbit from U.S. soil in only its second attempt. They're also the only U.S. commercial space company with a rocket ready to take customers to space in the highly desired 1,300 kilogram payload lift class.
And now, as we look ahead to 2023, we can expect more Alpha rocket launches, and they're also hard at work on the Blue Ghost mission.
As part of NASA's Commercial Lunar Payload Services Initiative, Firefly was awarded a contract. This will deliver 10 scientific instruments to the lunar surface in 2024 via, voila, the Blue Ghost lander. Will Coogan is the lunar lander chief engineer, and he's working on Blue Ghost's first mission.
Yeah, so this is a trade show mock-up of our lander. This is full scale, so this is exactly how big the flight model will be.
Tell me more about those 10 payloads. What exactly will you guys be doing up there?
They're doing everything from proving out a global positioning system all the way out to the moon, which is way past where the GPS satellites are. And they're actually looking all the way past the Earth to the GPS constellation on the other side. We're taking finer measurements to the distance of the surface of the moon than has been done since the Apollo era. We are playing with the regolith quite a bit. There's one drill that's going down pretty far into the lunar surface, and it's going to be measuring temperature gradients, also measuring new methods for moving dust across surfaces on the moon. Dust is something that gets on radiators and stops them from working. It gets on solar panels and stops them from generating power. So there's a device that's been created with no moving parts that can actually move dust off of or back onto surfaces.
My understanding is that the regolith is pretty hard material to work around. So how are you guys simulating that here on Earth?
There are different ways of doing it. In this case, for the payload, they are our customer. So we don't need to do any of the testing of the science of their payload. We just do the operation on the surface of the moon. We do have to, however, make sure that our environments are good for the payload. So we do things like test the vibration environment to make sure they'll be okay on the structure they're mounted to throughout launch. We do things like integrated thermal vacuum testing to make sure that they're going to be good in the environments through transit and then again on the surface of the moon. For us with dust, we actually have some lunar simulant that we've gotten from an organization in Florida. So it's not from the moon, but it's made to be as similar as possible to something that we'll encounter on the moon. And actually later today, you'll see some drop testing of our lander feet. And it shows how they interact with different surfaces. Today, I believe we are using either sand or concrete because something like lunar dust is actually hazardous to people. So we would need full-on hazmat suits, and we would typically do that testing outside.
And then maybe just like describe or explain to us some of these features.
Yeah, so again, this is all fake. We can show you some real parts over in the clean room, as well as around the corner there. But we have carbon fiber struts that we make and test in-house. We have aluminum honeycomb decks, again, that we make and test in-house. And those constitute the primary structure. We have 8 reaction control engines that run on bipropellant. So it's just a fuel and an oxidizer that combusts upon mixing. And again, we are developing those all in-house, and actually the team's out testing those right now, as well as a main engine that you probably can't see but is under in the middle. The 10 science payloads are mocked up on here, and they're distributed all around.
Oh yeah, like point out some of those.
I can point out this one right here. That is the Lexi payload. That's actually an X-ray telescope. It's going to be looking at the magnetopause of the Earth. So we're going to be on the surface of the moon, but pointing that back at Earth. For that, we have developed a 2-axis gimbal. It actually has to have 0.3 degree pointing from the surface of the moon. So in lunar gravity, we can't, gimbal a spacecraft like we normally would. So we had to create a mechanism to accommodate that. And then we have a couple other cool features if you look below. There's an extra leg that actually descends down to the surface. Just point it out. So this is the foot. The leg pushes that down. I said there's a payload that vacuums the lunar surface. So they actually use a little puff of gas to bring regolith back into a collection unit. Yes, there are 3 different solar rays. So the sun will rise on the far side, go over the top, and then come down and face this side until sunset. And then we will continue to operate for an additional 5 hours into the lunar night. Lunar night's a very challenging condition for a spacecraft. It gets down to about minus 170 centigrade, and there is no power source unless you bring a nuclear power source with you.
So what do you do?
So we actually make our own batteries. I think you'll get a preview of that shortly.
Okay, cool.
And we just carry a bunch of batteries to operate into the lunar night. And we're going to actually be imaging the sunset with one of the cameras on one of our gimbals. And there's a phenomenon that's supposed to happen where the dust actually levitates off the surface when the solar rays are parallel to the surface. So we're going to try and image that for NASA, and actually got a mission extension to be able to achieve that.
Of course, I wanted to see some of their work and testing in action, so Jordan Landell, a spacecraft primary structures engineer, showed me how they're working on the lander legs. And look at the setup. It looks like we're about to do leg day at the gym.
It looks like we have, a mini playground / weight room here, but what exactly are we looking at?
It's actually both of those things. We use it for our free time. So this is our single leg drop test stand. And so we've used this to put our landing gear through a pretty extensive testing campaign to both test and qualify the landing gear design. We've done about 50, 60 drops across 4 different surfaces. So lunar simulant with rocks, with big rocks, and then just a concrete paver even, just to go absolute worst case scenario. And also, like you said, with the weight room setup, we can do different weights as well to really get a good understanding of how the landing gear behaves and what kind of loads we're going to be driving into the spacecraft body when we touch down on the moon. And the design is obviously kind of first of its kind for us, and so we wanted to really make sure that what we did and the math that we did behind it all kind of lined up. And a big one too is just one of our requirements with NASA and our contract is we're not going to put more than 5 Gs of acceleration into the spacecraft body when we touch down. And so verifying that we can guarantee that under any landing condition is a big part of our contract. And so being able to demonstrate that we can do that and do so comfortably. Testing showed no more than 3 Gs. And so we feel really confident that when we touch down on the moon, it's going to be a safe and soft landing. Up here, we're able to tilt the test stand back and forth. So we can look at whether we're landing vertically or as if we were coming down a bit at an angle. And then this whole sled is on runners, so we can set different heights to represent different speeds when we're landing as well. And then obviously you touched on the weights, so we can look at, depending on how much propellant we've used throughout our mission, how heavy we're going to be when we come down. And then finally, our actual landing gear. So we've got a composite foot pad that was built in Briggs by our composite shop in-house, some Peak ankle joint, and then a 3D printed titanium ankle itself. And so within this sleeve, we have crush cartridges, which are just cylinders of aluminum honeycomb, and that is our shock absorber. And so when we come down, that takes up all that load. Go ahead, pull our safety pin out, stand back, and let it fly.
You ready?
Nice. We're on the moon.
Wow. Okay, that was good. So when Blue Ghost hits the surface, they want to make sure not to shake the payloads, which is why there are shock absorbers in the legs here.
This was our test, or our crush cartridge as installed when we put it in there. And then you can see how much compression we got upon impact. And so these crush cartridges allow us to absorb the load of landing without driving that load into the lander itself. Next steps for us as we were doing testing, we basically lift this back up, pull the foot pad out of there, and we can see how much that crush cartridge compressed. And from there, with sensors that we've used on previous tests, we now can basically extrapolate kind of what loads the spacecraft would have seen depending on how much that compressed.
Our Firefly tour continues with an avionics overview, and Joseph Marlin is the spacecraft electrical engineering manager.
Our team is responsible for, first of all, working with the hardware designers to ensure that the avionics systems, that's the brains of the spacecraft, are designed for the mission as we need them to be and work effectively. And then we're responsible for taking those designed avionics systems and integrating them into the satellite. That starts with physically securing them to the satellite, mating all the harnesses to and from the satellite, and then doing all the integration testing to make sure that all these complicated systems talk together correctly.
Is that what they're working on behind me here?
Yeah, so behind me, we have a number of engineers who are working on ensuring that the Blue Ghost lunar lander avionics can talk to each other. So inside we have some automated test equipment. We want to make sure that everything's being read correctly, but not only is it being read correctly, the correct decisions are being made on that information. So we have 10 NASA payloads on there. I think my personal favorite is LPV, that's the Lunar Planet Vac, because I think it's very charming that we have a vacuum in the vacuum of space. It uses compressed air, compressed nitrogen to shoot lunar moon dust up into a sampling chamber where it can analyze it further. Moon dust is extremely sharp. It sticks to everything because there's not a good ground source on the moon, and so anything with a charge attracts it, and it destroys bearings, it destroys joints. It's hazardous for astronauts to breathe. And so a lot of our mission is going to be looking at how to characterize that regolith, understand how it works, so that we can protect the humans and equipment that we send up on future missions.
So here it looks a little bit like a scrapyard. But I mentioned before when we were looking at the trade show model that we make aluminum honeycomb cores. What we have here are some aluminum face sheets over aluminum honeycomb core. It's just like you saw in the drop test, except this one hopefully is not absorbing any impact from landing. And then there's another sandwich panel on the bottom side here. This particular build came from our structural qualification model. We built a mock-up of the lander using flight-like structures, took it out to a large test facility that can just, shake the heck out of it and simulate launch conditions. We intentionally shook it past the point of where the analysis said it would start experiencing some failures, and then we're able to cut apart the panel, show that those failures did occur where we had predicted, and just gave us high confidence going into the flight build now that everything's going to work.
But one of the many challenges of going to space is that space is an extremely unforgiving environment. And not only is it extremely hot and then extremely cold in these very rapid time periods, it also does not benefit from the protective envelope of the Earth's magnetic field as much. As a result, there's a lot of radiation. And so one of the challenges of making avionics, these flight computers that control the spacecraft, is making sure that the radiation, the trapped particles in space and the galactic cosmic rays and solar flares do not damage the fragile avionic boards, the computer systems that run the spacecraft. And so what we do is we make test boards where we test each of the individual chips that we're planning on using. We screen them with radiation facilities on Earth, and we basically shoot them with protons or heavy ions, which are larger molecules that can cause more damage or different types of damage. We screen them to make sure that they will not have any permanent damaging effects. So it's pretty much a given in a very high-speed environment that certain chips are going to at least reset. We don't expect for this type of mission, this class of mission, a completely radiation-hardened environment where there's no effects from radiation. But we do want to make sure that anything that happens is recoverable. It can immediately bounce back and continue operating like nothing happened. So we take these to radiation facilities like at Texas A&M or Penn State or the Mayo Clinic, and we use their, for example, at the Mayo Clinic, it's used to treat cancer patients. But at night, when the patients aren't there, we actually go in with our avionics board and use the exact same equipment to shoot our avionics boards. And so this is an example of a test board. These are just chips that we are screening to see how they behave in a radiation environment. And then we take the results of this and apply it to our designs.
And how are they holding up so far?
They've been great. We have not had any parts that we have wanted to use that we've not been able to use. So we've been finding some. And this is one of the examples of how New Space is looking to take the innovations and lean on the science and technology that's being developed across the terrestrial world and apply it to space. So these are parts that were not meant for space. They are not priced like they are meant for space. They are used for cars and computers here on Earth. But by doing this extra screening, we can use these highly available, low-cost chips to expand access to space.
And we couldn't get a thorough snapshot without taking a trip to the clean room, or at least outside of it.
It's a nice thing actually about Firefly. You get to wear a lot of hats. So in addition to my work on the structures team, I'm also our lead mechanical integration engineer for Blue Ghost. So behind me is our clean room. It's a 2,500 square foot ISO 8 clean room where we are going to be doing all of our assembly and integration of the Blue Ghost lander. You can see we already have our COPVs on hand. Work is being done. The fluids team is performing a lot of welds on various components. You can see on this tank right here, we've got our heaters going on as well. And not in there quite yet is the structure itself. Right now that's being manufactured at Briggs with our composite shop. That's, kind of our bread and butter here at Firefly, working with composites. So they're putting together the panels there, and then those will be brought down here for us to start integrating components onto the lander. That structure will start coming down in pieces. We'll get one panel at a time. We'll start putting some of the fluid components on, welding those together as well. Then once both of our panels are ready, the tanks go on, those decks get stacked, and all of the struts in between get bolted in. Then at that point comes electronics. So the avionics and those various components that Joseph just talked about, those get brought on board, bolted down and everything. Finally, all of our harnessing that's done in the harness shop just down the hallway here, that gets routed. Our electronics team, the test side of assembly, integration, and test will start coming in, performing safety mates, making sure everything's connected, all hooked up. And then once we can do that, everything's plugged in on the lander and we can start running functional tests from some of the ops centers just outside the clean room here. Like I said, it's ISO 8 threshold, so it keeps it really clean in there. And that's actually also where we'll store all of NASA's payloads that they're bringing to us. So as they get delivered, we bring them in, do usually a set of functional checkouts, make sure that their hardware is still working as expected. We'll do a fit check with some of the bracketry or the panel that they're going to be mounting to make sure all of that lines up. And then they're stored in their case in a locked cage in here in the obviously environmentally controlled setting in there. So we have a lot of confidence that those payloads are staying safe and clean. All of our welds in the fluid system undergo radiographic inspection, visual inspection, and a leak check as well. So as the fluids team completes welds on various components, we have a vendor come in and they usually spend a day or so, probably once a week, if not twice a week, radiographically inspecting our welds, making sure that all of those are nice and tight. And so when that propellant gets in there, it's staying there.
I recently interviewed Anne Chinnery, who obviously works here now, but she was in the very, very early days of SpaceX. So it must be cool to see some of those parallels.
Yes, we have a lot of former SpaceX folks as well as other veteran New Space folks, and it's been very helpful, I think, to get all their lessons learned and fold them into this new company.
How long have you worked at Firefly?
I've been here over 2 years now. My first year was spent at Vandenberg, building our launch pad there.
Were you in the space industry before Firefly?
No, actually, I'm one of the rare people who transferred in from a different industry. Before this, I worked for buses, monitoring the engines on large motor coaches. And then I worked monitoring substations, actually, in the electrical power grid. And both those things have a lot of similarities to monitoring a launch pad for all the different valves and equipment that has to be operated on a launch pad. So, and now I'm monitoring satellite buses and building those up. So I've been able to bring a lot of the technology that these very established industries have and bring it into this new space ecosystem where we're trying to learn and grow rapidly. And it's been really good to have an outsider's perspective. But obviously, I've been able to learn quickly, and now we're making a moon lander. Well, always wanted to work in space. Never thought I could, but was encouraged to just shoot for my dreams, and it actually worked out. I think it's that human desire to explore. There are so many things we've learned from the International Space Station that we have used to improve life on Earth, and so many things that we've learned from the ISS that we are now applying to the moon. It's going to be the same thing over again for the moon. Everything that we do to make sustained human presence on the moon, we're going to then apply to Mars. And so we're building up this library of science, this library of innovation, but what we're able to do is move super fast. And so we're building up these libraries of innovation and science that we then, whenever we're looking to go to Mars, we can pull a book out of that library and say, okay, what's our solution for water storage in a sub, 100 degrees Celsius environment? Well, we already figured that out for the permanently shadowed regions of the moon. So we can just, pull that book out of the library and apply it to Mars.
We hope to have Alpha be more of a production line and going at a pretty regular cadence before the Blue Ghost lander flies. This is still about a year and a half out.
So I want to give a big thanks to Firefly for letting us interview some of the talented minds working behind the scenes here. And if you guys like this video, please make sure to click that thumbs up. Subscribe to Ellie in Space if you haven't already, and I'll see you in the next video.